So just to recap these one more questions from the other day. When you solve a logarithm, what are you solving for?
Exponent.
You're solving for an exponent, which is a really unique situation that you're solving for an exponent. Again, you consider that for most of your childhood life, most of your growing up, you're always solving for x as a base, right? X is normally a base. That's how polynomials are. That's how rational expressions are. So then we're really flipping it around to say 2 to the power of x equals 5, which is just such a completely different question, which becomes much, much harder because typically when you solve for an exponent, it is a decimal that is infinitely long. So, it's a much harder problem. And again, whereas algebra had been solved for thousands of years before now, going all the way back to ancient Greece, solving for an exponential like this really only became a practical science in the 1500s, 1600s. So that's what a recent technology this is, to solve for an exponent. Okay, so we talked about reading things like log base 2 of 16. What's 3 different ways that you can read that? When you see this expression, what's one way to say it?
2 to what is 16?
Yeah, very good. It's a question. 2 to the what is 16? So that's a question. What's another way to read it?
Log base 2 of 16.
Yeah, the actual words, you'd say log base 2 of 16. And then one more way, what does this represent? What equation does it represent?
2 to the power of what is 16.
Yeah, it represents 2 to the x equals 16 right there. So that's 3 different ways for thinking about that expression. And in mathematics, just being able to flexibly interpret that in different ways gives you a lot of power and ability. If you can look at an expression and think of it in different ways, you can approach a problem from different ways. Okay, so we talked about converting expressions. So if you had something like 3 to the x equals 81, that's called exponential form. Whereas if you wanted to switch it into log form, you would keep the first number the same. That'd be log base 3. And make it teeny tiny down below. And then you switch to x and 81 and say log base 3 of 81 equals x. And you'll notice, when you solve a logarithm, you're solving for an exponent. This whole logarithm, log base 3 of 81, is equal to x, which is literally the exponent. So it's not just, some conceptual, idea that would say this is an exponent. It really is an exponent. This is the exponent. You could even be so wild as to write down 3 to the power of log base 3 of 81 is equal to 81. Like if you type that, so look what I did. I just took that expression, I put it in for x. If you type that into your calculator, it would tell you 81. Right? So that expression there really is the exponent on 3 that would give you 81. It looks a little weird when you write it like that, but it's true. Okay, so what else did we talk about last time? Oh yes, we did our domain. So that was, and we did all of those problems too. I mean, we looked at all the different ways to take an expression and rewrite it in order to solve it. So we said, if they give you an exponential expression, switch it to a logarithmic expression. If they give you a log expression, switch it to an exponential expression. So we went through all of those, solving exponential and log expressions. Then we talked about domain. So let's remind ourselves that when you have domain, there are now 3 things you can't do on your calculator, right? 3 things that your calculator would give you an error message. So 1 is you can't divide by 0. That's an error message because it's undefined. 2, you can't square root a negative. That's an error message because it's imaginary. And now we also know you can't log 0 because your calculator would say undefined. And you can't log a negative because your error message, your error message would say imaginary. So these are all things that you can't do. So what is our test then? Here your denominator can't equal 0. So that's one test. Denominator can equal 0. Here you can't square root a negative, which means you can square root 0 or positive. So we say radican has to be greater than or equal to 0. And then here, you can't square root 0, you can't square root a negative. Square root. You can't log 0 or a negative, which means you can only log a positive number. So that means the argument has to be strictly greater than 0. So take a look at those 3 domain tests, right? These domain tests are just there to tell you when you'd expect your calculator to give you an error message because you're doing something fundamentally wrong versus when your calculator is giving you an error message because you typed something in wrong, right? That's 2 very different situations. Your calculator will give you an error message if you simply make a typo, but your calculator will give you an error message for sure if you try to do one of these things, which you're not allowed to do. Okay, so yeah, we did domain, and then we talked about graph transformations. Oh, and then we did properties of logarithms. That was exciting. So we saw various ways in which you could expand and rewrite. So let's clarify that. We can, in mathematics, we talk a lot about simplification, but it's just as powerful to simply be able to rewrite something, to rewrite it in a different way, even if it's not necessarily quote unquote simpler. So we had a few rules there. We said log of the product was the sum of the logs. That was one rule. And then we had the log of a quotient is the difference of the logs. And then we had the log of a power, which you can bring the power out front and call that n times log a. So these are three rules that we can use to simply rewrite a log expression. It's not necessarily making it simpler, it's just changing it into a different form that could be more manageable and simpler to solve a larger problem. Okay, so we last time finished expanding all of those. So just to clarify, a really helpful thing that we did towards the end there, even though you can just use these rules one at a time, let's just take a look at, say, number 5 real quick. Who can tell us what we said was a general shorthand rule about how to rewrite this thing all at once? There was something about terms in the numerator and terms in the denominator. Exactly. Any term in the numerator is a positive log, and any term in the denominator is a negative log. So I can just take that expression right now and rewrite it as positive log x squared, and then negative log 81, and then negative log y to the 4th. Right? Because x squared is in the numerator, it's a positive log. 81 is in the denominator, it's a negative log. Y to the 4th is in the denominator, so it's a negative log. Was that all log base 3? Okay. So from here, then, you would proceed to finish solving, or finish simplifying. Not simplifying, finish rewriting. So for instance, I could pop that 2 out in front, I could pop the 4 out in front, and then I could ask the question, 3 to the what is 81? So I would finish this as 2 log x minus 4 log y. Now, we call this process expansion. And we said it's expansion because we went from a single log with a complex argument with multiple parts to now we have multiple logs, but the argument is simple. Right? So you see how that flip-flops? Here we have only one log with a complex argument. Here we have multiple logs, but the argument is just one item each time. Okay, so this is called expansion. So everybody, let's take a look at the next page and try compression. When you compress a statement down into one. We'll just do a couple of these. It's pretty straightforward, and I think you might even find it easier than expansion because we can use this handy rule that a positive log is a term that goes in the numerator, and a negative log is a term that goes in the denominator. So take a look at that first one, log x, log y minus log z. Just go ahead and write down one single log expression. So log base 2. And then if it's a positive log, put that argument in the numerator. If it's a negative log, put that argument in the denominator. So for instance, where would that x go, Jackie? Yeah, the x would go in the numerator. And Urban, where would the y go? The y term? This y term is a log that is positive, so it would go in that. Yeah, in the numerator. And then where did the z term go in? No. Okay. And then that's it. It's already compressed. That's the compressed form of the logarithm. So instead of having multiple logarithms with single arguments, we now just have one logarithm with multiple arguments. So in number 8, we're going to essentially do the same thing. You know, you have a positive log and 2 negative logs. So you know that when you're done, you're going to have a logarithm with a fraction that has 1 term in the numerator and 2 terms in the denominator. But what do we have to do first before we can compress it all together? What do we have to do first? You know, we have to pop those exponents back on top of the argument itself. Everything has to go inside the log first before you can compress it. So when I have here 1/2 that log 3, 1/2 log 3 of x minus 2 log 3 of y, and then minus log 3 of z. First, we would need to put the number back inside the argument. So we would have log base 3. By the way, what's x to the 1/2? Actually, 1/2 is just the square root of x, so we might as well just go and rewrite it like that. Because when you put 1/2 on x, that's x to the 1/2, so that's the square root of x. Minus 2 on the y, that's just y squared. And then minus log z. Now we can go ahead and rewrite that as a single log with one big open parenthesis. And you put each term where it belongs, depending on if it's positive in the numerator or negative in the denominator. So Jessica, where would the root x go? Numerator or denominator? Yeah, numerator. And then Joseph, where would the y squared go? And the denominator. And Brandon, where would the z go? Denominator. Yeah, denominator as well. So that's it. That's our compressed log. Number 9 works the same way. So let's leave that one and move on to number 10. Number 10 is a little bit of a clever problem. Because we have a log and then just the number 3. Right? We've only been talking about how to compress lots of log terms into one log term, but is 3 a log term? Yeah, I mean the number 3 is just the number 3, right? But can we rewrite it as a log?
Yes.
Yeah, we can. And again, let's really talk about this word rewrite. Rewrite is so valuable. Like for instance, I can take the number 1 and I can rewrite that as 2 halves or 17/17. Or I can rewrite it as 5 to the 0 or 112 to the 0, right? There's a lot of ways to rewrite the number 1, for instance. But I could also rewrite 1 as log base 5 of 5. Because how do you read this as a question? 5 to the what is 5? And the answer is 1. So I mean, oh my gosh, there's so many ways to rewrite a number. So let's consider the number 3. How would I rewrite that as a log? And what kind of log do we want? Is it log base 5? So 3 is log base 5 of what? Now don't shout it out just yet. What do you think, folks? How can we rewrite 3 as a log base 5? We're saying here 5 to the what would be 1. But what we know for sure is here, let me write this backwards, because it might be, I always think it's easier to see the log on the left. So how do we rewrite this? This is really, yeah, it's left to the right equals middle. So this expression really says 5 to the 3rd equals what? And what is 5 cubed? Yeah, what, 25? So what we know now then is that the number 3 can actually be rewritten as log base 5 of 125. And then check it. Like look at it. See, make sure, does that make sense? 5 to the what is 125? 3, which is the number 3. So watch what we can do here. You can take your log base 5 of x, and then instead of writing 3, you write log base 5 of 125. And now you do have 2 logs. And now you can go about compressing them. I've got a positive log and a negative log, so that's just a single log base 5 of x in the numerator, 125. That problem was really neat. It really showed the potential of rewriting. Rewriting, wow. Rewriting is such a helpful concept that you could take something and write it in a different way. So everybody try that on number 11. In number 11, you have log base 7 of x, and then log base 7 of x minus 3. And then we're subtracting 2. So your challenge is, how can you rewrite the number 2? And what kind of log do you want it to be? Yeah, we want to rewrite 2 as log base 7 of something. Now, look, I hope you see how helpful it is to write it down as a goal statement. Like it's a 2, but we wish it was a log base 7, because then they'd all be the same log and we could compress it. So what we're really saying now is, I wish I could rewrite 2 as a log base 7. And you could go one step further in making this even more clear to your brain. You could say, I want log base 7 of blank to equal 2. And then just literally write that down. I want log base 7 of something, question mark, to equal 2. And by writing that down, you give your brain input that you can actually look at and manipulate. And you can say, oh, well, that means that left to the right equals middle, that means 7 squared equals question mark. And therefore, my question mark is 49. And so I can rewrite 2 as log base 7 of 49. And now you can go about compressing it. So go ahead and give that a shot. Compress the whole thing. I would definitely do it. Yeah, nice. I'm glad to see everybody using parentheses in that numerator, excuse me, Josh. To keep the x and the x minus 3 separate. So here, everybody can check their answers real quick. So we have positive and negative logs, so we know we'll have a fraction. We've got x, we also have an x minus 3, and then at the bottom we have a 40. And that'd be it. Okay, number 12, everybody can cross out. It's a really good bonus question. It's actually really interesting and fun, but it goes a little bit beyond what we need to do. Okay. So that was called expansion and compression, and it demonstrates the potential of rewriting. That sometimes in mathematics, you know, you want to solve a problem. So you're given a problem, and you don't see a way forward. You don't know how to walk forward with the problem. So sometimes the most helpful thing you can do is move sideways, rewrite it some other way. And maybe then you still don't know how to move forward. So you rewrite it differently again. And maybe finally then you know how to move forward, but only after rewriting an expression a few times. Okay, so we have one last rule here with logarithms, which really concludes our ability to solve any logarithmic problem. This is a really great rule. And you use it quite often, well, every time that you're solving an actual log equation. Because you'll notice that at this point, we haven't really solved any equations. We've just been rewriting things according to definitions. But what we're about to do is start solving equations. So our last rule, everybody, jot this down up at the top of your page so you can see it. Remember, we've been writing things down like this. Base to the exponent equals answer. That's how we wrote it the first few days. And then we convert that into log form by writing log base b of a equals e. Right? So the b stays the same, then the e and the a switch, and that's converting from exponential form to log form. So the change of base rule tells us how to compute something like this on your calculator. So just for some motivation, your calculator only has a log button, which is log base 10. Which means you can only solve equations of the form 10 to the x equals a positive number. Your calculator also has an ln button, which is technically log base e, which means you can solve equations of the form e to the x equals a positive number. But what we would like to be able to do is calculate something like log base 2. That's what we'd like to be able to do. We'd like to be able to solve any log expression, regardless of the base, and even especially if the base is not a 10 or an e. So how would we solve log base 2 of 50? Well, we already talked about solving a problem like this by saying that really is the question 2 to the what equals 50, and you don't have to write all this down. But the only way we've seen so far how to solve 2 to the what is 50 is the sandwich technique, where you'd say, well, 2 to the 2, 4, 8, 16, 32. 2 to the 5 is 32. And I want 2 to the x is 50, and 2 to the 6 is 64. So I have a sandwich here. And I'd be able to say, well, it's 2 to the 5 point something. So then I'd start guessing, and I'd say, well, it's 2 to the 5.5. And then I would find out what that number is, and I would work to find another sandwich. And once I do, I could bump out another decimal, and I could keep on finding the answer. So far, all we really know is that if I wanted to solve log base 2 of 50, the answer is going to be around, I don't know, 5 point something. So let's just remember that, 5 point something. That's the best we can do. Whereas, now this last rule we're going to learn, the change of base formula. Change of base formula states, change of base states that if you have log base b of a, where b is any number and a is any number, you can actually write that down as log base 10 of a divided by log base 10 of b, or natural log of a divided by natural log of b. They both work. And these are both buttons that your calculator knows, right? So even though your calculator doesn't have a log base b button, your calculator does have a log button, which is log base 10, and it does have an ln button, which is log base e. And by simply taking, and literally I'm going to say, the big number versus a little number, and by that I mean the regular font number and the little tiny number that's written down below, you do log of the big number divided by log of the tiny number, and that will actually give you the answer. So let's try it. In my example here, I have log base 2 of 50. And I already kind of know the answer is 5 point something. But now if I use the change of base rule, I just say log 50 divided by log 2. And again, that log right there is the log on your calculator. So everybody type it in your calculator. Type log 50 divided by log 2. And make sure you close those parentheses, because your calculator will automatically put a parenthesis after the word log. And so you need to make sure to close the parenthesis. So just to show what kind of calculator error you can get into, if you type log 50 and don't close the parenthesis, and then, so if you type this, log parenthesis 50 divide by log 2, and you don't close the parenthesis, it's going to give you the wrong answer of 2.22. But you'll notice I didn't close my parentheses. And if you don't close your parentheses, you'll get the wrong answer. You have to close the parentheses and write log 50 parenthesis divided by log 2 parenthesis. Okay, isn't that wild? I mean, that's something to really take notice, that parentheses are so important. That gives you the answer, 5.643. So, on your calculator, did everyone get 5.643? Okay, now immediately try ln of 50 divided by ln of 2 and see what you notice. And again, you have to close those parentheses. Yes, the same answer. So whether you use the log button or the ln button, totally up to you. Matter of personal choice. The change of base rule works either way. And it does indeed give us the answer to this equation, 2 to the x equals 50, 2 to the 5.6439. So change of base rule is really helpful because it allows you to calculate any log on your calculator. So let's just try a few of those real quick. Type these all into your calculator. So if you have log base 3 of 12, that would simply be log 12 divided by log 3. This is calculator practice more than anything, to make sure that you're typing in that parenthesis. Also notice, depending on how geeky you feel, you could come up with an estimate before you actually hit enter on your calculator. You can say, well, what 3 to the what would be 12? I mean, it's 3, 9, 27. So it's the answer between 2 and 3. So when you type that in your calculator, it should give you an answer between 2 and 3. Yeah, 2.26. Try number 4. Yeah, in fact, go ahead and try all of these. And I'm just going to walk around, see if anybody has any questions. So that'd be a log 18, log by log 5. Number 5 and 6, the whole point is to let you know that this works even if you're dealing with fractions or decimals. So that one would be log of 10 divided by log of 4. And 6 would be log of, actually, what is that, 3/5? Log base 3/5 of 1,000 would be log of 1,000 divided by log of 3/5. My go-to is just use the log button. But if you'd like to use the ln button, or switch it up, sometimes use log over log and sometimes use ln over ln. You can feel free to do that. Is that open? Is it working? Yeah. Is it working? Josh, oh, I don't know. Well, but this one should still work. Do you have your log function? Well, yeah, there you go. Yeah, it's working. In fact, I wouldn't be surprised if yours might even be able to change the base. But not that you can use that calculator on the test, but it can. Oh, okay. Somebody in the room, I bet, has a calculator that can actually change the base. Does it work? Does it work? Yeah. Okay, yeah. Although, if you have a TI, then you don't. I think TIs don't allow you to change the weights. Did it work? Yeah, very nice. Yeah, log of 10 divided by log of 4. That's right. Yeah, that's okay. That's a negative number. Okay, let's get some answers. What did you get for number 4? So that log 80 divided by log 5? 2.76? 2, okay. Did anyone else get that? Okay. How about for number 5, log of 10 divided by log 4? Celine, what did you get? Yeah. Now, notice, you might say, oh, negative number. I feel a little uncomfortable with that. You know, isn't it so true that sometimes you hit enter on your calculator and you see a number and you're like, I'm uncomfortable with that. Sometimes we get answers that don't seem right. But consider the power of 4. We're saying 4 to the what is a 10th. Anytime at all, you can just take your number that is the base and go ahead and write out your powers, you know, and just kind of explore that number and say, well, what is this number like? So 4 to the 0 would be 1, and then 4 to the negative 1 would be a 4th, which is 0.25. And then 4 to the negative 2 would be a 16th, which I don't know. What is a 16th? As a decimal. There's my calculator. 15560. There we go, 0.0625. And notice, what are we trying to say? Log, so 4 to the what is a 10th, which is 0.1. So that would be here. If I want 4 to the something to be 0.1, that would be in between those two, and therefore in between negative 1 and negative 2. So a negative answer is perfectly natural and normal for that. Negative what?
Is it supposed to be negative?
Oh, sorry, 6. I just misheard you. I'm old. My ears don't work very well. Okay. And then the last one, what did you get for number 6? Sarah? 5, 6? Okay.
2.
Both 2.
Sorry.
All righty. Well, folks, that's the change of base rule. So why is this helpful? Because now we can truly solve any exponential equation that we're given. Okay, so we spent multiple days developing our definitions of logarithms, definitions of exponential expressions, various different rules and properties, and now we can finally go about solving some interesting looking equations. So this is the real meat and potatoes, the real bread and butter, the real stuff here. This is what we've been working to do. So everyone turn the page, take a look here. I'm going to show you 2 different techniques for solving exponential equations. Okay, we have 2 techniques. And you'll see up there that they give you a couple steps there, and that's fine. We can read that later, but let's go ahead and take a look at the first problem. So I'm going to show you for number, let's say, 1 and maybe 1, 2, 3, one particular approach to solving an exponential equation. Okay, one approach is that if you look at the numbers, the base numbers, mind you, okay, these base numbers right here, if you can look at the base numbers and see that they're both powers of the same number, you should rewrite it as powers of the same number. So for instance, are 2 and 8 both powers of the same number? Yeah, 2 is 2 and 8 is 2 cubed. So we can go ahead and rewrite this as 2 to the 4x equals 2 cubed. So this is why it's helpful to have just a general familiarity with powers of numbers, especially powers of 2, 3, 5, and 10, so that you can just look at 8 and be like, hey, I recognize 8, that's 2 cubed. So now here's how the rule works. Yeah, you equate, as a rule, equate the bases. So we just did, we equated the bases, we made the bases the same number. Then equate the exponents. This is like your mission. So if you can equate the bases, then you can equate the exponents. So now that I clearly see that 2 and 2 is the same base, I can say that 4x must be equal to 3. And I just drop the exponential equation, I just rewrite it as 4x equals 3, and then I just finish solving this simple, normal algebraic equation. There's no exponentials involved here at all. So I would divide by the 4, and I'd say that my answer is x equals 3/4 or 0.75. So we just solved for that x. Are we right? Yeah, plug it in, right? Absolutely. Always. Anytime you do algebra, you're not done until you plug it back in. So if you plug in 0.75 where 4 is, 4 times 0.75 is 3, and 2 to the 3 is 8. So yeah, it's true. That's really the answer. So that's our method. Let's try one more. In number 2, we have 5 to 2x minus 1 equals 125. Now this one's pretty straightforward and simple because just looking at those two bases, what are they both powers of? They're both powers of 5. So I can leave the one on the left, 5 to the 2x minus 1, and then the one on the right, that's 5 cubed. And again, as a rule, equate the bases, equate the exponents. So now that the base is both 5, I can say that 2x minus 1 must be equal to 3. It's just by sheer logical force. But if I want both of these sides to be the same thing, then whatever x is, it has to simplify out to equal 3. So now I say 2x minus 1 is equal to 3, and I move my 1 over, and I say 2x is equal to 4, and I divide my 2 over, and I say x is equal to 2. And as always, you're never done with algebra until you take that number and you plug it back in. And plugging it back in, you can often just do visually. So 2 times 2 is 4, 4 minus 1 is 3, 5 to the power of 3, 125. So it worked. Now, you'll notice, because we solved for x in the exponent, we just did the conceptual logarithm, right? We solved a logarithm, we solved the exponent. However, we never actually used logarithms, right? So we didn't introduce the word log to our work. Let's just try one more here, because I want you to see a full diversity. Number 3, I'm just going to show you how to rewrite it. So number 3, you have 4 to the 2x, and you have 1 over 2. So look at 4, look at 1/2. What are they both powers of? They're both powers of 2. So you can rewrite 4 as 2 squared. And you can rewrite 1/2 as 2 to the negative 1. So those are on the first page of the first packet we did with logs. And again, it's just so important that you just have familiarity with how to take a number and rewrite it as a power of another number. So what can we do then over here? What's our exponent rule? It's just one more of many, many, many formulas that we should all know, such as x to the a times x to the b is x to the a plus b, and x to the a divided by x to the b is x to the a minus b, and what we want is x to the a to the b. So when you have an exponent raised to an exponent, you multiply the exponents. So this gives us 2 to the 4x equals 2 to the negative 1. And I'm going to stop right there. You can finish solving that, but you can see now, since the bases are equal, the exponents must be equal as well. And so you set up your new algebra equation. Number 4 is kind of fun. Again, we're just going to rewrite it. You have 2 to the power of x cubed minus x equals 1. So again, look at the bases. What are they both powers of? They're both powers of 2. That's obviously a power of 2 because it's 2. How is 1 a power of 2? It's 2 to the 0. So all this just requires that number fluency. That you can just look at a number and say, oh yeah, that's a power of 2. And it is a power of 2, so it's there. And you would say, since the bases are the same, the exponents must be the same. And I can't help wanting to show this one. How would you solve x cubed minus x equals 0? What can you do to that thing? You can take out an x, first of all, so that's x outside of x squared minus 1. And then what would you do with x squared minus 1? Can you factor it? It's the difference of squares, right? X squared minus 1, you could rewrite that. I'll put it right here. That's really x minus 1, x plus 1. So look at that. What a fun problem. It starts as an exponential equal to 1. You have to recognize that 1 is 2 to the power of 0. Once the bases are equal, you set the exponents equal. And then you have to take a cubic and factor it all the way down. It factored pretty nicely. And then by the zero product rule, you know that x is either equal to 0, 1, or negative 1. And those are the 3 solutions to this exponential equation. Are we right? You still need to go back and plug those 3 numbers in one at a time and check to make sure that it really does work. Now, what we just saw there is this particular approach, which is that if you can equate the bases, then you can equate the exponents, and you can solve an exponential problem without ever introducing the word log. However, you won't always be able to equate bases. So number 5, I'm going to leave for you all to do. I think you can all see that 3 and 81 are both powers of 3, because 81 is 3 to the 4th. So now let's go on over to number 6. And this is a really exciting moment. Again, we've spent 3 days of talking about logs, all so that we can solve a problem like number 6. This is what we were leading to. So everyone take a look. We've got 3 to the 2x is equal to 5. Really exciting. Now remember, what are we trying to do? Trying to solve for x. You know, what number can I plug in right there such that when I multiply it by 2 and then raise 3 to the power of that number, it actually turns out to be 5. So, right, yeah, so we can't use that approach at all now, because 3 and 5 are not both powers of a single number. Right? 5 is not a power of 3, and 3 is not a power of 5, so we can't use that approach at all. Instead, what we always will do is if they give you an exponential problem, convert it to a logarithm. And if they give you a logarithm, convert it to an exponential. So go ahead and let's just convert this to a logarithm. So the 3 stays the first number, so log base 3 of 5 equals 2x. Notice what we did. We got that x out of the exponent. X is no longer in an exponent. It's not trapped up there in an exponent. X is just a normal old x being multiplied by 2. And in a moment, we'll divide off the 2 and we'll have our answer. So let's go ahead and do that just to feel good about ourselves. Divide off the 2. And actually, instead of dividing by 2, let's write 1/2. Let's multiply both sides by 1/2. Because that'll look a little nicer. So over here, the 2 and the half cancel out. We have x equals 1/2 log base 3 of 5. Now, first of all, that's the answer, right? That is the answer, 1/2 log base 3 of 5. But just looking at that, we have no idea what the actual number is, the decimal number. So now, write the 1/2 as a fraction, and how do you write log base 3 of 5 as a fraction? Using the change of base rule, which I should write somewhere up here. Change of base rule, log base b of a, through a log a, or log b. So we would say that's log 5 over log 3, where that log is base 10. It's the log on your calculator. So before I type that into my calculator, first of all, notice the way I wrote this. I can go ahead and cleanly say, well, x is equal to log 5 over 2 log 3. And that's exactly what we'll type into our calculator, making sure you use parentheses, right? You got to wrap the numerator in parentheses and then wrap the denominator in parentheses to make sure that your calculator is doing the right problem. So if I do parenthesis log 5, divide by parenthesis 2 log 3, you'll get your answer. Now, folks, notice there's actually a parenthesis around 5 and 3, right? So in your calculator, what is it going to look like in your calculator? It's parenthesis, log, parenthesis, 5, parenthesis, parenthesis, divided by parenthesis, 2 log, parenthesis, 3, parenthesis, parenthesis. All right, so type that into your calculator. And what do you get? I didn't get that. Am I wrong? What's log 5 divided by 2 log 3? Oh, that is what you got too? What was that? I wonder what I'm doing. You need parentheses, folks. You absolutely, this is not optional. You need a parenthesis around the entire numerator. You need a parenthesis around the entire denominator. If you typed in, just to show as an example, if you typed in log 5 divided by 2 log 3, notice that I do not have parentheses around the numerator and I don't have parentheses around the denominator. Your calculator thinks you just said log 5 divided by 2 times log 3. And is that what we wanted? No. So, okay, so using your parentheses, folks, the way I typed it here on the board, what did you get? 0.73. Yeah. So that's our answer. X is 0.73. Now notice that's what x is, right? So when you plug x into that, it's really 2 times that. So that times 2 is really 1.46. And then 3 to the power of that, 3 to the power of that, 3 to the power of that gives you exactly 5. So if you check your work by plugging it in, it'll. Okay. Does it surprise you how many parentheses you need to use on your calculator? Oh, maybe yes, maybe no. Okay, well. All right, let's try another one, folks. So that was number 6. Let's try number 7. We have 5 to the power of negative x equals 2. Well, once again, this is just a wonderful example of why this whole theory of logarithms was invented. Because someone wanted to be able to say 5 to what power would equal 2. So they gave it to us in exponential form, so we need to convert it to log form. So we'll immediately take that and rewrite it as log base 5 of 2 equals negative x. And remember, at this point, that's really a negative 1x. And traditionally, I think most people would divide off the negative 1. But how can you do it besides dividing off the negative 1? We talked about another way. You just multiply both sides by negative 1. Because multiplying both sides by negative 1 doesn't divide off the negative, but it does cancel it nevertheless. So x is really equal to negative log base 5 of 2. That's the exact answer. So if you write down negative log base 5 of 2, that's the exact answer. All the decimals are wrapped up inside that expression. And if you handed that answer to anybody, they'd be able to get all infinite many decimals for themselves. Whereas we're going to go ahead and get a decimal, so that'd be negative log 2 over log 5, and type that into your calculator. Negative. Now again, you can never go wrong by wrapping the entire numerator in parentheses and wrapping the entire denominator in parentheses. So it would actually look like parentheses, negative log, parentheses 2, parentheses, parentheses, divide by, parentheses, log, parentheses, 5, parentheses, parentheses. Yeah, parentheses is such a long word. It's 4 syllables, my goodness. Okay, so what did we get? Did anyone get negative 0.43? Yes. 0.676, so I'll just call that 0.4307. See, the negative 0.4307, that's a close answer, and the More website would take it. Close enough for government work. But this was the exact answer. It has infinitely many decimals wrapped up inside of it. This is an approximate answer, which has the first 3 decimals correct. How does everybody feel about this? What questions would you like to ask so far? Then, kind of looking ahead here, we're going to continue solving these. We have 2 more exponentials we're going to solve. And then we're going to solve some log equations. And then we'll do some applications. Leave that there. Let's do number 8. We have 8, that's 2,000. E to the 0.1x? Equals 4,000. Now folks, as a general algebraic strategy, recall a few weeks ago we did a problem like 5 plus 2 root x minus 1 equals 7. Our goal was to get rid of the square root sign. And how do you get rid of the square root sign? You have to square it. But we can't just square both sides right now, because that would lead to lots of complications over here. What do you have to do first? What, Jay? Yeah, you have to subtract off the 5 and then divide off the 2. And what we called that was isolate the root. Before you can actually solve this problem, you have to isolate the root. That is, get it by itself on one side of the equation. So after I subtract off the 5, and then divide off the 2, so that's 2, then divide off the 2. So that would be root x minus 1 equals 1. Now I can square both sides, and there will be no complications. It'll just cancel the root, and then I can finish solving. And so x equals 2. The key is you have to isolate the root. Same thing in exponential problems. Before you can actually solve and convert from exponential to log form, you have to isolate the exponential. So write that down. And I would put a box around it. Isolate the exponential. And kind of notice the analogy here. With the square root problem, you wanted to cancel the square root by squaring, and you could only do that by first isolating the root. Here, we want to cancel the exponential expression by converting it into a logarithm, and you can only do that by first isolating the exponential. So, we divide off the 2,000, and that gives us the e to the 0.1x equals 2, and now our exponential is all by itself, and we're ready to go. We have base to the exponent equals the answer. So now we can convert that to a log. So log base e of 2 equals 0.1x. And by definition on your calculator, what is log base e? It's just ln. So you can just write ln2 equals 0.1x. So ln2 you can just type into your calculator directly. You just type ln2. Okay. This whole concept of rewriting and the power behind being able to be flexible and how you write things down and rewriting things. Notice, folks, that right now, in one reality, I could divide off the 0.1 and look at what the answer looks like. The answer is natural log 2 divided by 0.1. Yeah, that's fine. You can type that into your calculator and you'll get the right answer. But notice, if instead of writing natural log 2 equals 0.1x, what if I rewrote it as natural log 2 equals 1/10 x? Right? All I did was rewrite 0.1 as 1/10. Anybody say, well, what benefit is that? Well, now when I solve for x, since there's a fraction in front, I multiply both sides by the reciprocal, which is multiplying both sides by 10. The 1/10 cancels, and now I think we have a much cleaner answer. 10 natural log 2. What do you think? Doesn't 10 natural log 2 look better than natural log 2 over 0.1? I think it does. I mean, here you're doing a fraction and a decimal. Right here, it's just a whole number. So again, the power of rewriting. Instead of 0.1, writing 1/10, and then you got a really nice clean answer. Even easier to type into your calculator as well. Okay, so what was the answer, folks? 10 natural log 2. Did anyone else get 6.93? Is that what you got? All right. So number 14, I'd like to show you a really exciting graphical solution to this. Really exciting. Now, oops. We go to Desmos. So look at what this problem is asking. They're saying, when is this exponential bigger than 3,000? So what does that mean in terms of, remember when we did graphs and we would say f of x is greater than 0 versus f of x is less than 0? What did f of x greater than 0 mean? Yeah, when is the graph above the x-axis? Whereas what did f of x less than 0 means? And when is it below? So what is this equation or inequality really saying? When is this whole exponential graph what? Yeah, above 3,000, right? So let's take a look. Here, I'm going to graph, I'll have to zoom out quite a bit to get to 3,000. Okay, I'm getting there. So the first thing I'm going to type in is 1,000 times 1.005 to the, what is it? 12. Parenthesis 12x. Okay, so when is that exponential above 3,000? Now, the first thing I'm going to have to do is redo my units. Oh, this is so hard. I'm going to go from 0, did I type 0? 0 to simply 100. Ooh, 10 looked even better. Did I get to 3,000? Where's 3,000?
Yes.
Where's 3,000? Oh, it didn't graph because I didn't write y equals. Keep in mind, if you want it to be a line, there we go. Ah! So take a look here, folks. When is the graph above 3,000? Using interval notation, thinking about domain, when is my exponential graph above the line 3,000? Anywhere to the right of, what number is that?
18.
Yeah, 18.53. Okay, so that's our answer. The answer is this exponential graph will be above the line 3000 anywhere to the right of 18. So let's just remember that now and actually do the algebra, because I want to show you something very subtle here and maybe a little unfortunate. So you know how sometimes you do algebra and it gives you an answer that turns out to be extraneous? Right? Sometimes you get an answer that's extraneous. You do the algebra, it says the answer is 2 or 5, but then you actually plug in 2 and it doesn't make it true. So we have to be really careful about algebra and really remind ourselves, algebra is not done until you plug the answer in. You know, algebra is not done until you actually check and confirm. So everybody, let's try 14. We'll write down 1,000 times 1.005 to the 12x is greater than or equal to 3,000. So, as we said, what do we have to do first? We have to isolate the exponential. So I would box it. Oh, I need an X, don't I? There we go. So box it. We need to get that by itself. So I'm going to divide off the 1,000. And that gives us 1.005 to the 12x, which is greater than or equal to 3. Now we do have an exponential, so base of the exponent equals the answer. Now I can rewrite it as a log. Remember, that's pretty much always the way. If they give you an exponential, rewrite it as a log. So now I'm going to say log base 1.005 of 3 equals 12x. And instead of dividing by 12 and putting a 12 underneath all that, I think, again, it'd be better to multiply both sides by 1/12. Again, this is just flexible thinking. You know, even if your whole life you've been dividing by 12, try it this way. Try it this way for a while. Instead of dividing by 12, try multiplying by the reciprocal. So now what we really have is 1/12 times, using the change of base rule, log 3 over log 1.005. And in other words, then I can rewrite that as just log 3 over 12 log 1.005. So everybody, once again, try typing that into your calculator correctly. In your calculator, it'll look like this: parenthesis around the numerator, parenthesis around the denominator, and parenthesis around each argument. So it would look like parenthesis, log parenthesis 3, parenthesis, parenthesis, divided by parenthesis 12, log parenthesis 1.005, parenthesis, parenthesis. So try typing that in and see what you get. Everyone good? What we expected, the 18.3559. Right, now notice, I kind of stopped doing this correctly up here. It was greater than. So that's greater than, greater than, greater than, greater than. Did I do that right? Now, is that correct? Is x greater than or equal to that? Was that what the graph showed? Yeah, x was greater than that number. Okay, so that worked. However, in this next problem, I could be wrong, but I think when we do the algebra, we're not going to do it right now in class, but when we did the algebra here, the inequality was pointing in the wrong direction. And so it was only by graphing it that we saw what the real direction was, whereas the algebra failed because the inequality symbol was pointing in the wrong direction. So you know how when you do algebra with an inequality, if you multiply or divide by a -1, what do you have to do to the symbol? You have to flip it. Well, something goes on with exponentials and logarithms as well. That's, oh yeah, I can see why. When you do algebra on an inequality with exponentials and logarithms, sometimes you have to flip the inequality as well. There's a rule there. I think they even put it in the packet. But you can verify for yourself. You do the whole algebra, and you can always just graph it and see for sure which way it's supposed to go. And I think that's a really good idea, is always graph and check yourself by asking yourself, when is the graph above the the line 3000 to the right. And so that way, even if the algebra gives you the inequality pointing the wrong way, you would verify it by graphing. Okay, so we'll skip number 16 in the interest of time. And we are ready to try something different. We're going to try some logs. Before we do, does anybody have any questions you want to ask? Or comments? Or requests? Everybody's just ready to go? So, what do you see here? Like, let's just look at this first problem. So you've got log of 3x minus 1 equals log of 4 minus x. How would we go about solving this? Because remember how I told you that if they give you exponential, convert it to log. If they give you log, convert it to exponential. But there's a log on both sides. So we can't use the definition of log to rewrite it because there's a log on both sides. They are both log base 10. Yeah. Exactly. It would have to be the case that since this is log base 10 and that's log base 10, you've got the same base on both sides. So whatever's inside has to be the same. You know, if they're both log base 10, whatever's inside there, those two things have to be equal. So consider that's exactly like what we said about equate the base, equate the exponents. When you had something, just imagine if I gave you the problem 2 to the 3x minus 1 equals 2 to the 4 minus x. Right? I use the same variables here. So since the bases are the same, then by logical force, it must be the case that 3x minus 1 is equal to 4 minus x. Must be. And likewise here, since we have log base 10 on this side, and we have log base 10 on this side, it's the same base on both sides. And then here we would say equate the logs, right? It's the same log on both sides. Therefore, equate the arguments. So it must be the case that 3x minus 1 is equal to 4 minus x. So everyone in this case, go ahead and write down that general rule. Equate the logs. So make sure that the logs are the same on both sides. Equate the logs. Equate the arguments. So for these first two problems, 1 and 2, the fact that there's a logarithm in the problem is pretty immaterial. It really doesn't matter at all. Because we're just going to look at it and say, well, since it's the same log on both sides, I can just go ahead and say that 3x minus 1 must be equal to 4 minus x. And then you just keep solving from there. So I'm going to bring my x's to my right. So that's 4x minus 1 equals 4. Push my numbers to the right. Sorry, bring my x's to the left. Push my numbers to the right. 4x equals 5. And then divide up 4, and x equals 1.25, or 5/4. You could almost say that's not even really a log problem, right? The log is just there in the initial setup, but you immediately just equate the arguments with each other and do normal algebra. So the same thing works in number 2. The algebra is just a little more exciting. So in number 2, we have log base 5 of 18 minus x squared equals log base 5 of 6 minus x. And again, in that case, since the log base 5 is the same base on both sides, we say equate the logs, therefore equate the arguments. So now I know that 18 minus x squared is actually, it must be equal to 6 minus x. And now we fall back into all of our old behaviors of solving quadratics and solving equations and just doing all the algebra that we know how to do. So how do we solve a quadratic? What's the first thing you want to do with a quadratic?
Set it equal to 0.
Yes, both of those things mean the same thing. Set it equal to 0, move all the terms to one side. Because if you move all the terms to one side, it'll be equal to 0. I'm going to move the x squared over to the right. So I'm going to move my x squared over here. I'm going to subtract the 18 over there. And so now I have 0 equals x squared minus 1x minus 12. And can we factor that? 1 multiplies to make 12, that adds to make 1? Yeah, I'm going to do a factor table real quick. Never hurts to make a factor table. 1 and 12, 2 and 6, 3 and 4. I want to multiply to make a negative 12, so it has to be a plus times a minus. So 1 is plus, 1 is minus, and therefore it's plus 3 and minus 4. So now we have 0 equals x minus 4, x plus 3. And so by factoring the zero product rule, we know that x has to equal 4 or x has to equal negative 3. Are we done? Selene, why not? You have to plug it back in, right? And this is the weird part about algebra. All the algebra you do, even if you do it right, you're still not done because you have to plug it in because one of those solutions could be extraneous. Both of those solutions could be extraneous. We don't know yet until we plug it in. So let's try, let's plug it in. So if I plug in 4, that'd be log base 5 of 18 minus 4 squared is 18 minus 16, which is 2, equals 6 minus 4 is 2. So yeah, that one's true. Log base 5 of 2 is equal to log base 5 of 2. That's true. What if I plug in negative 3? That'd be log base 5 of 18 minus 3 squared is 18 minus 9, which is 9, log base 5 of 9, equals log base 5 of 6 minus negative 3 is 6 plus 3, which is log base 5 of 9. Okay, so both of them turned out to be correct. We could have never known that, though, until we actually plug in the answer and check. I suddenly think about the fact that like somebody makes you dinner, somebody makes you a really good peanut butter and jelly sandwich, and you look at it like, man, that looks like a really good peanut butter and jelly sandwich. Is it a good peanut butter and jelly sandwich? You don't know until you eat it. Right? It might look really good, but it could be terrible. And that's kind of like an extraneous solution. Somebody makes you a nice meal, you look at it, you're like, ooh, nice meal. But no, you eat it and it's awful. And you're like, man, that was an extraneous meal. It looked like it was going to be good, but it wasn't. All right, we have more problems to do. These are different types of problems, so let's take our break. It's 9:04, let's come back at 9:14. Yeah. Good luck.
Mr. Chief?
Yes.
I won't be able to stay like the half of the class, so we just have to like use this on there's the last two.
Yep.
And then the things online packages.
Yeah, you can watch all the videos on the Moore website, and then I posted the practice test solutions on Canvas as well.
Okay.
Sure. All right, is everybody ready for some excitement? We are now going to solve some log problems. And the good news is, it's relatively straightforward and simple because it's always just a matter of converting back and forth between an exponential expression and a log expression. So take a look here. We have number 3, log base 3 of 7 minus 2x equals 2. See, only at face value does this look complex. You know, someone walking down the street, they'd be like, oh, you're that kind of bad. But really, just look at it. It's exponential. This is logarithmic form. So left to the right equals middle. So it's just 3 squared equals 7 minus 2x. That's very, very simple and straightforward. Just all you really need is the definition of how to switch from a log to an exponential. So now we have 9 equals 7 minus 2x. And I'm going to subtract off the 7. Now I have 2 equals negative 2x. And divide off the negative 2. And you have x equals negative 1. This problem and problems like it are such a great example of how so much in math is actually really simple and straightforward, provided you know the definition, right? So if you don't know the definition of a log, you look at this and just say, oh, that's, that was hard. I don't know how to do that. That's possible. But the fact is, once you know the definition, that this is really the base, that's the exponent, and that's the answer, you just rewrite it from a log to an exponential form, and then it's just basic algebra. So it's deceptively simple. Even number 4. So that was number 3. Here comes number 4. You have log 1/2 of 2x minus 1 equals negative 3. So we've been talking about this idea of rewriting. And if you know definitions, then it's simple to rewrite things in other ways that make it easier. So for instance, one definition we should all know is that a negative exponent means reciprocal. And watch how that plays out in a variety of ways. So if I have 1/3 to the negative 1, it simply means do the reciprocal of 1/3, which is 3. Because if you flip 1 over 3, you get 3 over 1, and that's just 3. Likewise, if I have the number, well, yeah, no, that's enough. Oh, yeah, no, a fraction. So like 5/2 to the -1, that again is just the reciprocal. The answer is 2/5. So once you know the definition of a negative exponent, it's really easy. You just say, oh, that's the reciprocal. You just flip the fraction. So take a look at this one. We have 1/2 to the -3 equals 2x minus 1. So that's 1/2 to the -3 equals 2x minus 1. So first of all, what started out as a log problem is not really a log problem at all. It's just a simple exponential expression. And so now look here, we have 1/2 to the -3. That's actually 2 instructions right there. That negative means do the reciprocal, and then the 3 means cube it, right? So the negative means take the reciprocal of 1/2, which is 2, and then the 3 means cube it. And again, those are the definitions. That's what they mean. So now we have 2 cubed equals 2x minus 1, and so 2 cubed is just 8 equals 2x minus 1. So then you add the 1 over, and you have 9 equals 2x, and then divide up 2, and you get x equals 4.5. So again, at a conceptual level, I really want to stress this idea that mathematics only appears tricky at face value sometimes. But provided you know all the definitions involved, it's just a matter of step-by-step applying the definitions, and then the problem solves itself. So take a look at number 5. We've got natural log of x squared minus 99 equals 0. So what do? We need to apply some definitions. What's one definition we could apply? Victor, what's the definition we could apply?
I'm not sure.
What's the definition of ln? Yeah, log base e. So let's apply that definition, now log base e of x squared minus 99. Now what can we do? I mean, you can call it a definition, but the definition of how to switch from a log form to an exponential form. So how would I rewrite this now? Left to the right equals middle. So e to the 0 equals x squared minus 99. What's another definition we can apply? Anything to the power of 0 is 1. So now we have 1 equals x squared minus 99. This is all the standard algebra now. You move the 99 over, and you get x squared equals 100. Square both sides, and x is plus or minus 10. Are we done? What's the last thing we have to do? You have to plug it in. You always have to plug it in. This one we can pretty much just do looking at it. If I plug in 10, 10 squared is 100, 100 minus 99 is 1, and the natural log of 1 is 0. You can type it in your calculator, ln1, see that it's 0. Or you can remind yourself, is ln1 equal to 0? Is that a true fact? To see that it's a true fact, you have to apply the definition that ln is log base e of 1 equals 0, and then convert from log form to exponential form. Is e to 0 equal 1? Yeah, so that's true. And then if I square negative 10, squaring a negative 10 also gives 100, and 100 minus 9 is 99 is still 1. Okay, so that works. Everybody go ahead and do number 6. So in number 6, you've got log. What's that definition? And away you go. Do the entire problem. Make sure you specify what the base is. Convert from log form to exponential form. Simplify it. There'll be a quadratic. Solve the quadratic. Once you solve for x, see if your answers actually work. Okay. Thanks very much. Oh, I would just continue rewriting the whole time. That's what I'm doing. And so now, in order to, yeah. Okay. Yeah, perfect. So that would be 10. You wrote these down. You were intending to still write the original problem, right? But just base 10. This is log base 10, but I started with 6. You switched those two. I'll still keep it as 1. You see what I mean? Okay. So this is really long base 10. So that means left to right is 0. So it's really 10 to the 1 equals x squared minus 3x. That is your 1, but it's not log base 10 of 1 is this. It's log base 10 of this is 1. You switch those two things, but you're not allowed to switch them. It's you switch them when you convert it to exponential. Okay, does that make sense? Okay. Yeah, remarkably, you still ended up where you were supposed to go. It's just that this line right here is not true. Okay. Yeah, there you go. And how do you solve quadratic? Yeah. Yeah. Right. Is that equal to 0? Very nice. That's it. And 10 to the 1 is just 10. And so then move all your terms to one side and solve your quadratic. Got it, Erica. 10 1 is 10. Very good. I like how you're writing all that out. The one to move that 10 over first. To set it equal to 0. Right? Yeah. So this is really log base 10. Okay. So here's the principle. So the first thing you want to do is put 10. You can either write it as teeny or write it as log base 10 of equivalence equal. So this is still log form. But now we're switching to exponential. So it's going to be left or right. So now 10 to 1 equals x minus 6. Because it's the definition. ln on your calculator, by definition, ln is log base e, and log, by definition, is log base 10. That's the definition. So now we have x squared minus 3x equals 10. I would move all the terms over to one side. So that it's equal to 0. So you have 0 equals and from here it's just a quadratic factor. Solve for x. The work system? Oh, great. Yep, that looks good. There you go. The work happy. Yeah, good. Yeah, you're getting there. Super. Okay, folks, so let's compare. The definition of log is log base 10. That's just the definition on your calculator. Log means log base 10. So now, converting to exponential form, left to the right equals middle, 10 to the 1 equals x squared minus 3x. This is a quadratic because there's an x squared. So we always move all the terms to one side. So 10 to the 1 is just 10, so I minus the 10 over. So now I have 0 equals. Now again, folks, when we say move all the terms to one side, that automatically sets it equal to 0. And why do we want it equal to 0? So that you can factor it, so that you can use the zero product rule to say this times this equals 0 means either this equals 0 or this equals 0. So x equals 5 or x equals -2. Now at this point, we're not quite done yet because we have no idea if one of these or both of them is extraneous. So we take both of them and plug them in and see what happens. So if I plug in 5, that would be log base 10 of 5 squared is 25 minus 15 is 10. That's a true statement. 10 to the 1 is 10, 1. 10 to the 1 is 10. So that's true. But now what if I plug in -2? That would be log base 10 of -2 squared is 4, -3 times -2 is 6. Hey, that's also true. Log base 10 of 10 equals 1. So great. Both of them lead to a true answer, and so both of them are correct. All right. So we have a few more problems here, and these are really good. All right. These are sophisticated, slightly tricky problems that use all the rules that we've used so far. So I'd like to model them for you up there on the board. Write down every step with me, and stop me if you have questions. All right. So take a look at number 7. Looks tricky, right? You look at it, you're like, oh, that looks tricky. So log base 125 of 3x minus 2 over 2x plus 3 equals 1/3. So they gave it to us in log form, so we should convert it to exponential form. So now we have 125 to the 1/3 equals this. So left to the right equals middle. So we have 125 to the 1/3 equals 3x minus 2 over 2x plus 3. So again, definition. What does 125 to the 1/3 mean? Square root of x is x to the 1/2, and cube root of x is x to the 1/3, and any nth root is x to the 1 over n. So 125 to the 1/3 means the cube root of 125. Now what does that mean? Yeah, it means what times itself 3 times will equal 125. And again, you should be familiar now with 125. Just looking at 125, you're like, oh yeah, 125 is not 5 cubed. Right? And so the cube root of 125 is 5. So now we have 5 equals 3x minus 2 over 2x plus 3. Now just look at what we did here. This is, the steps. You know how when you write steps and you're showing work? Every time you show a step, you're just applying a definition. You're saying, well, by definition, I can convert a log to an exponential. By definition, raising something to the 1/3 is taking the cube root. By definition, the cube root of 125 is just 5. So now we just have a normal basic algebra problem, and it's not a log anymore. It's not an exponential anymore. It's just a normal algebra problem. So how do we solve for x? Yeah, multiply both sides by the denominator, because we don't want a denominator. That complicates things. So to get rid of a denominator, you cancel the denominator. So we're going to multiply both sides by 2x plus 3. On the right, it cancels out. So that makes our life easier. There is no more denominator. On the right-hand side, we distribute the 5, and we get 10x plus 15. This is such a wonderful problem, because you start with complexity, and baby step by baby step by baby step, we're approaching just something that looks like a normal, simple algebra problem. So we move our x's to the left. Oh, sorry. We move the 3x to the left. So now we have 7x plus 15 equals 2. We move the 15 to the right. So now we have 7x equals negative 17. Yes, we do. And therefore, x equals negative 17 sevenths. Again, when you're doing algebra and you get to an answer like negative 17 sevenths, your brain might say, oh, I did something wrong. That can't possibly be the answer, negative 17 sevenths. So how do you know if it is or isn't? You just have to plug it in. Now, folks, plugging it in is something of a bummer, right? We have to plug negative 17 sevenths into that. You wouldn't want to do it by hand. You'd want to do it with a calculator. So I want you all to appreciate what that would look like in your calculator. You would type in parenthesis, 3, parenthesis, negative 17 divided by 7, parenthesis, minus 2, parenthesis, divide by, parenthesis, 2, parenthesis, negative 17 divided by 7, parenthesis, plus 3, parenthesis. Right? That would be the proper way to plug negative 17 sevenths into your calculator. That's a whole lot of parentheses. You have to train yourself to put parentheses around fractions and always wrap the numerator in parentheses and wrap the denominator in parentheses. So if you do all that, you get 5. So then you have the problem, log base 125, 5 equals 30. And is that true? That's true, because left to the right equals middle, 125 to 1/3 equals 5 is 5 equals 5, and it's true. But again, you have to type all that in your calculator first to even see that it equals 5. And then you know that's 5, so you have this, which is true. And then you know that your answer is correct. Did I do that correctly? Did I just make a big assumption by not actually typing it in? Should, quote unquote, I type it in? Yeah, you should always type it in. There's 5. All right. All right. 6 minus 3 log base what? 5 of 2x equals 0. So what should we do? I didn't specify yet how to solve a problem like this, but I'm wondering if you could take a guess. Take a swing at it. What's that, Josh?
I was just repeating what you said.
Oh. Yeah, well, I heard a couple different things. Divide, who said divide? Divide what? Well, you're not going to divide the 6. You're going to subtract the 6 and then divide by the -3. Because what are you trying to do? You're trying to isolate the log. Exactly right. You isolate a root, you isolate an exponential, and you isolate a log as well. Right? You need to get that thing by itself first so that you can then apply the definition and convert from a log to an exponential. So we subtract off the 6. So we got -3, and then the log, we get 6. You divide off the -3, and so now we have log base 5 of 2x equals 2. Now I want you to notice, once you isolated the log, this is rather trivial. Like this is super trivial. Like now that you know how logarithms work, how do you really read this as an exponential? Left to the right equals middle. It's just 5 squared equals 2x, which is 25 equals 2x, which when you divide off the 2, is just 12.5. So again, I just want to reiterate the message that no single step up here was tricky. All you needed to solve this problem was to know to isolate the log, and once you isolated it, to know how to convert from a log form to an exponential form. And really, truly, every single step along the way, very simple. Subtract the 6, divide the -3, convert to an exponential, square the 5, divide by 2. Every individual step is very simple. All right. We have our last 2 equations before we do some word problem applications, which is everybody's favorite. So, number 9. I'll do it like this. Number 9. Now, you will have a problem like this on your test. Log base 3. Log base 3 of x minus 4 plus log base 3 of x plus 4 equals 2. So what do we do? What definition can we apply? And just think, we've got this whole universe of definitions to apply. Like square root of x is x to the 1/2, or anything to the 0 is equal to 1. Or, gosh, what are other definitions? Just how to convert from a log to an exponential. Well, notice what we're doing right now. What are we doing here? What are we doing? We're adding logs. What definition do we have that applies to adding 2 logs together? We had a rule that the log of AB was equal to log A plus log B. So again, you look back into your toolbox and you say, what's a possible definition I could apply in this situation? That's almost constantly what you're doing in math. You're constantly just looking and saying, what would apply? You know, what could I do here? I have a definition that says that I can add 2 logs together and then I take the log of the product. And so that's what you do. We go ahead and say, well, it's the same base. So I can add the 2 logs together by multiplying the arguments. So that gives us log base 3 of bracket x minus 4, x plus 4. And then what? Yeah. Once the log is isolated, rewrite it in exponential form. So now we have 3 squared equals, now how could I rewrite x minus 4, x plus 4?
It's perfect square, so it would be x minus 16.
Yeah, difference of squares. This is the product of conjugates, so it's the difference of squares, so x squared minus 16. So now I have 3 squared equals x squared minus 16, which is really 9 equals x squared minus 16. And then we add the 16 over. X squared equals 25, square root both sides, and x equals 5 or negative 5. Now, are both of those answers correct? We don't know. And I hope maybe that's something that you take away from all of this, our time together, is that just because you finish the algebra problem, you're not done. You have no idea if those answers are right or wrong. A, because you might have made a lot of mistakes, and B, because they could be extraneous. I mean, you have no reason to think that you're done right now, because you could have made a mistake and they could be extraneous. So now we plug them back in. So if I plug in positive 5, That'd be log of 5 minus 4 is 1, plus log of 5 plus 4 is 9. And then I'd have to ask myself, is that equal to 2? So you'd have to evaluate both of these in your head. 3 to the what is 1? Yeah, 3 to the what. So again, you can write it down. 3 to the what is 1? 3 to the 0 is 1. So that's 0. 3 to the what is 9? 2. And is 0 plus 2 equal to 2? Yeah. Okay, so that's true. 5 is definitely an answer. But what about negative 5? If I plug in negative 5, that gives me log base 3 of negative 5 minus 4 is negative 9, plus log base 3 of negative 5 plus 4 is negative 1. And so now what are these? Selenium? Yeah, you can't log a negative. That's a domain error. If you type that into your calculator, it would be an error. It'd say domain error, imaginary, non-real answer. So this is not correct. Negative 5 is extraneous. So there's actually only one solution, and it's just 5. All right. Last equation that we'll solve, we have natural log plus 1 minus natural log of x equals 3. So what can we do? What definition can we apply? Yeah, we see a log minus a log. And so from your tool belt, you would just look at it and say, well, I've seen a log minus a log before. That's natural log of a over b equals natural log of a minus natural log of b. So we have a formula for this. We have a way of rewriting the difference of two logs as a single log. And that gives us the natural log of x plus 1 in the numerator, x in the denominator. And what's the definition of ln again? Yeah, just log base e. And then it's in log form, so we convert to exponential form. So e cubed equals x plus 1 over x. And at this point, e cubed is a little bit of a bummer, because e cubed is not a whole number. Right? If you type it into your calculator, it's going to be some terrible thing like 24 point something. Well, we just keep going anyway. How do we solve for x? We don't like that x in the denominator, so we're going to multiply both sides by the denominator. So we cancel the denominator, so now we have e cubed x equals x plus 1. And here's where it's a little mind-bending, because we're not used to seeing an e cubed as a coefficient. Everyone would appreciate how you'd solve this problem right now if e cubed was a number like 5. What would you do if it was just a 5? Yeah, you just subtract just as always. And so 5 minus 1 is 4, and you have 4x equals 1. But notice, even though all of us would write 5 minus 1 is 4, how else could I write it? I could write it like that. You all agree that even though it's obvious that we would all say 5x minus 1x is 4x, you could write it like that. You could subtract the coefficients 5 minus 1 and put the x after it. Right? This is just another way of rewriting. So here I have e cubed x and 1x, and I subtract 1x from both sides. How could I rewrite that? Like that. It's a little weird. Might feel awkward at first, but you can do it. Say that again.
How come the negative 1 isn't outside of the parentheses?
Why did I not put the x in front of the parentheses?
Inside. Because it's e cubed x.
Well, here, let me do that in 2 steps. So sorry, thank you. So this would be e cubed x minus 1x, right?
Oh, okay.
And then I'm just taking an x out, so it's e cubed minus 1, and I leave the x in the s. Did that answer your question?
Yes.
Okay, so now x is being multiplied by this, so we divide by this, and we end up with this very interesting looking answer. X is equal to 1 over e cubed minus 1. Now, Brandon, does that work? What's your question?
I was trying to understand why, I kind of thought the same thing, Sheila, and I think we both were thinking that you were gonna take that X out.
It's because he ended up dividing the X out.
Yeah.
He just didn't see it.
Well, yeah, so like e cubed x minus 1. All right, is everyone okay from here?
Yeah.
Then yeah, you can take x out.
When you wrote it originally, I don't think there was thought about having to take out the X
Oh,
because
okay.
it's e cubed X minus 1X. So I was like,
Nice. But now, is that better?
Yeah.
So you take out the x and I just put it at the end. Okay, sweet. Thanks for asking. Okay, now, we're looking at this answer, we're like, well, is it right? So what would you do? Probably what I would do, because I don't necessarily want to substitute that in for x up there, I'd probably come up with a decimal. Okay, so watch how we do this here. I'm going to get a decimal. So that'd be, on your calculator, folks, 1 divided by parenthesis e caret cubed minus 1. So you get that decimal, and so that's 1 divided by parenthesis e cubed, and then minus 1. I got the decimal 0.05239, so 0.052. So I have a decimal. It's just a decimal approximation. That's not the exact answer. It's just 4 decimals worth of an answer. So now I'm going to take my equation, natural log x plus 1 minus natural log x, and I'm saying it should equal 3. Right? If I plug in the correct value for x, it should equal 3. Well, I don't want to plug that whole thing in for x because that would be awkward. But I could plug in 0.0524, which is a decimal approximation, pretty close to the real answer. And so when I do, I should get something that's pretty close to 3. So let's do that. If I do natural log of 1.0524 minus natural log of 0.0524, and I'm only using a decimal approximation, so it's not going to exactly equal 3, but I should get something pretty close to it. 1.0524 minus natural log of 0.0524, and I get 2.99992. And that's enough to give me confidence that it's correct. Right? I didn't actually plug in the real answer, but I plugged in a decimal estimate that was close enough, get me close enough to 3 to say, okay, yeah, that's right. All right, folks, we've come a long way. We have an hour, that's great. So we built up all of this logarithmic theory to be able to answer the original question. Okay, going back all the way to the beginning, solve for an exponent. What if you want to solve for an exponent? So the basic example we gave was, what if I had 2 to the x equals 50? That's a fairly uninteresting, non-real world question. Like, who cares what 2 to the x is 50? But there are lots of equations in the real world that have exponents in them that are very important, such as compound interest. So if you have a equals p, 1 plus r over n to the nt, which I think we've seen this in this class, then this is a very interesting real question that you could ask. So p is the principal that you invest, so I'm going to invest some money. And then r is the interest rate, so maybe at like 5% interest, maybe $1,000 I'm investing. N is the number of times compounding. So maybe you get interest compounded monthly. Okay, so I'll say 12 monthly. And then T is the number of years that the money sits in the bank, right? And then A is the amount you have at the end. So just consider that you have this problem. You say, I want to invest $1,000 principal. I'm going to earn 5% interest. My interest is compounded monthly, so 12 times. And I'd like to ask the question, how many years until I double my money? Okay. You've all heard the phrase double my money. Like, you hear about get rich quick schemes, like you can double your money. Well, how long would I have to let the money sit in the bank in order to double my money? So what's my question? The question is, how long until I double my money? Which variable am I asking about? That time. I'm asking to solve for t. Now watch, I'm going to take this formula and plug everything into it that I know. So, got my formula here. A equals P, 1 plus R over N to NT. And I'll plug in everything I know. I want to solve, oh no, actually I know N. I'm going to invest $1,000 at 5% interest, compounded monthly, So then that's 12t, and I want to double my money to get $2,000. Okay, so now look at this equation, because this equation asks a question. This equation says, if I invest $1,000 at 5% compounded monthly, how long until I double my money? So, what are we trying to do? We're trying to solve for an exponent. We're trying to solve for an exponent. And this is a very natural, real-world question in which you would want to solve for an exponent. And the only way you can actually solve for an exponent is if you take a logarithm. So I'm going to go ahead and solve this one, just because we've already set it up. We might as well know. So what I have now is 2,000 equals 1,000. And then, oh darn, those numbers aren't very good. I wish I had chosen something else, like a 3% interest. I'm going to do 3% interest. Does anyone care if I change that to 3% interest? Besides, that's more realistic these days anyway. Interest rates are very low. Okay, so now I'm going to solve this problem. So that's 0.03. So that's really 1.0025, all to the power of 12t. Okay, so what do I do? Yeah, and specifically our first goal is isolate the exponential, divide off the 1,000, so 1,000 divided by both sides, that's just going to be 2. And notice, this is kind of fun, this number 2 now represents the fact that I want to double my money. How much money do I want? 2 times as much. So now that's 1.0025 to the 12t, which I'm going to actually write this as equals 2, because I always prefer to see my exponential on the left and my answer on the right. So now this is an exponential. I can convert to a log. So this is log base 1.0025 of 2 equals 12t. And so instead of dividing by 12, I'm going to multiply by the reciprocal, 1/12. And so now I have 1/12, and by change of base rule, log 2 over log 1.0025. And I have now solved for t. And the only way you could solve for t in a problem like this is to use a logarithm. So what is my answer? T is equal to log 2 over 12 log 1.0025. So how long will that be? Remember, this is time in years. So that's parenthesis log 2 divided by 12 log 1.0025. Merely 23.13 years. So if I would like to invest $1,000 at 3% interest compounded monthly, and I'd like to double my money, all I have to do is wait 23 years. Which, I don't know about you, but I'd probably just get a job if I wanted another $1,000. Because I could probably make $1,000 in less than a month if I just go out and work. Okay, so that's just one motivating example of the fact that solving for an exponent arises naturally in real-world problems. So let's take a look up here. Turn the page. You've got applications of exponentials and log functions. So first of all, simple interest is I equals PRT. That's one formula for interest. But now here is the compounded interest formula, the one we just used. And furthermore, you have continuously compounded interest. Make a note right here, would you? In fact, everybody write this down. When we talk about compounded interest, you have this formula, and this is what you'll want to write. 1 plus r over n to the nt. So n is the number of times your interest is compounded. The word compounded means paid. So how many times is the bank going to pay you interest, okay, per year? So n equals 1 means it's compounded once, and you get paid once per year. So that's yearly. Okay, n equals 2 means they're going to pay you interest twice a year. So that'd be, what, bi-yearly? N equals 3 is never used because we don't have a word for 3 times a year. Do we have a word for 3 times a year?
Try.
Try what?
Try.
Yeah, I mean, I suppose you could, but nobody says. N equals 4, we do have a word for that. You get paid 4 times a year, and that's quarterly. We have 4 quarters in a year. N equals 5, we don't use. 6, you can say n equals 6, that'd be every other month. So what would that be, bi-monthly? Or is that semi-monthly? Oh, jeez, I don't know. Okay, nobody uses n equals 7, 8, 9, 10, 11, 12. It means 12 times a year, that's monthly. Now what do you go after that? Compounded. If you got compounded 365, if you're getting interest 365 times a year, how often is that? Daily. Now after that, I mean, how much more times can you get interest than once a day? You could get interest twice a day, I suppose. But look at our number 365. That's already a pretty big number. And if, let's just say, what if you wanted to get interest? Like you were really picky. You're like, I want interest every hour. Well, like what would that be? So 365 days a year times 24 hours in a day, that would be N equals 8,760, so hourly. First of all, no bank is ever going to give you interest. 8,765, 60 times a year. But that would be pretty cool because then you'd be like, I get interest every hour. That'd be pretty sweet. Well, what about every minute? If you're like, I want interest every minute. So you take that and multiply by 60 again. And then you're looking at 525,600 times a year, which is minutely. I want interest every minute. Could you be more absurd than that? What if you wanted interest every second? Every time your clock ticks a second, you want the bank to pay you a little interest. So that would be, that times 60 again, 31,536,000 times. And that's secondly. Okay, now I know I'm being silly here, but what I want to get to is that banks and financial people have actually considered this, and they said, what if we just go ahead and say let n equal infinity? Okay, what I want is a constant stream of interest flowing in to my bank account, like you turn on a faucet and water is just flowing in. So instead of a drip of water every hour, I just want a constant stream of water, right? And that's what n equals infinity would mean, that they're just slowly adding interest at a constant rate like a fluid. And when you let n equal infinity right here, when you let n equal infinity, you get a new formula, which is A equals P e to the RT. That's what this is. And they call that continuously compounded interest. Meaning, how often are you getting interest? Not once an hour, not once a minute, not once a second. Continuously. Just a stream of money flowing into your bank account. Now, it's not very much. It's like turning on the water, this least bit that you can, so that it's one stream of water. But you would be getting continuous interest, such that if you logged into your bank and looked at your bottom line, you would see the decimals moving, right, as the amount of money in your bank account was going up, up, up. Okay, so that's called continuous interest. You'll notice, what do these two equations have in common? Yeah, well, that's NT, that's RT, but they both have an exponent. And what is the exponent? Time. Time. Well, you also have N in there and you have R in there, but typically we're solving for time. We're saying, how long do I have to invest my money until I have this much? Right, so think about your own long-term planning. How long would I have to invest my money so that I have $20,000 in the bank? How long do I have to invest my money so that I'd have $1 million in the bank? This is all about retirement planning and planning for the future and saving money to buy a car or a house or whatever. Okay, well, that's just talking about the equations. Now let's go ahead and solve a couple of these. Now notice that there's instructions. Let's read those real quick. It says, find the amount A in the account as a function of the term of the investment, T in years. That just means write down the formula. Determine how much is in the account after 5, 10, 30, and 35 years. That just means plug in 5, 10, 30, and 35 for T. C, determine how long it would take for the initial investment to double. So we've already seen that question. That's our main logarithm question. How long will it take to double? Anytime you ask, how long will it take? That's a logarithm question because you're solving for time, which is in the exponent, so you have to use a log. And then finally, find and interpret the average rate of change in the amount of income. No, we won't do that one. Okay, everybody ready? Let's solve a couple questions about investing money in a bank. So number one. Now folks, let's all set up our problems in the same way. So first, everybody write down the formula. A equals P 1 plus R over N to the NT. Second, let's list out what all these variables are. So we have A, P, R, N, T. I simply wrote them in order in which I see them in the equation. So A, P, R, and T. Now let's write down what they all are according to the problem. So it says $500 is invested. Where do I put the 500? And P, that's my principal. Principal is what you invest. The A is the amount you have at the end. 500 is invested in an account which offers 0.75% interest. So where do I put that? Yeah, R. Now the thing is, R has to be a decimal, not a percent. So how do you convert 0.75% into a decimal? You can do it in a couple different ways. You can either, percent means per 100, which means divide by 100. So you can take that and divide by 100, or you can just move the decimal twice to the left. So that's really 0.0075. So in general, to convert a percent to a decimal, you move the decimal twice to the left. But it's handy to know that percent means per 100, which means divide by 100. And if you type 0.75 divide by 100, you get 0.0075. Okay, compounded monthly. Where do I put that information? Yeah, so n is the number of times it's compounded. Since it's monthly, that's 12. And then finally, t is what we want to solve for. How long? Now, a is the amount that you'll have at the end. So you'll notice that technically we have two unknowns right now, right? Depending on how you approach it, you're either going to put in some information for t and solve for a, or you're going to put in some information for a and solve for t. So for instance, if right now I said, how much will you have at the end of 5 years? I'd plug 5 in, and then I'd be able to calculate how much I have after 5 years. Or I could say, I want to double my money so that I have $1,000. So if I want $1,000 at the end, what would time be? So depending on what information you give, you're solving for the other one. So part A, everyone let's write this down. Part A simply wanted the formula. So our formula now is A equals 500, 1 plus 0.0075 over 12 to the 12t. You just plug everything in. And with that, you can even simplify it, which would be nice. So, everybody type, well, actually. Yeah, type that whole thing in your calculator and see what you get. Because we want to rewrite the whole parentheses as a single number. So we really have A equals 500 times 1.000625 to the 12t. Okay, we've now answered part A. Part A said find the amount A in the account as a function of the term of the investment in t years. So that's what we have now for part A. It's a function in terms of t years. If I really wanted to write it as a function, though, I wouldn't just write A. I'd write A as a function of t. Right now, that's in function notation. What's the amount of the money in the bank as a function of t years? So now whatever I plug in for t, I'll get my answer. So in part B, what did they want? Yeah, 5, 10, 15, and 30, and 35. That's a whole lot of t's. Jeez. How about we just do 5, 10, 30? I'm perfectly fine with that. So let's find A of 5, find A of 10, find A of 30. Notice how nice function notation is. Function notation is really nice. By just writing down A of 5, I've already communicated a complete sentence. Find the amount of money in the bank after 5 years. Find the amount of money in the bank after 10 years. Find the amount of money in the bank after 30 years. It's really concise language. Well, now you would all just use your calculator and plug that in. I think you can do it all in one swoop on your calculator. Please notice how to use parentheses. This would be 500 parenthesis 1.000625 parenthesis caret parenthesis 12 times 5. So your exponent needs to be in parentheses. If you don't put your exponent in parentheses, you'll get the wrong answer. So go ahead and solve all three. The great news is once you have that in your calculator for 5, you can just hit second enter and edit the 5 into a 10. And then edit the 10 into a 30. And you can get all 3 answers. Let's see. Doesn't look like it. What are those guys? Oh, really? Just something like that. Here's the answer. So I see how your exponent, you did put parentheses around both numbers. What I mean is the entire exponent has to be one parenthesis. So when you type in this exponent, it's 12 times 30. It's just a single parenthesis, 12 times 30. There. See, that's the exponent. After the caret, it has to be one big parenthesis. Say 12 times 30. Now that's how you do it. Does that make sense? Folks, as you type in all of your numbers, put the numbers up here so you can all see the answer. The first one was 519.10 if you round. Then A of 10 is 538.93 if you round. And A of 30 is 626.12 if you round. So still do that all on your own calculators, but you can go ahead and check to make sure that it came out that way. Oh, there's not 1.0. It's 1.000, but otherwise it's correct. Let's look at what we have. Oh, okay, no, this is fine. When you do the exponent, it's a single parenthesis wrapping the whole thing together. So you have two different parentheses. So what you really did was you raised it to the power of 12, and then you took that whole answer and multiplied it times 5. So what you really want is to just have a single parenthesis wrapping together the entire exponent. That'll work. So what you need here is a single parenthesis wrapping your entire parenthesis, your entire exponent together. Now, first of all, notice what I wrote on the board. I wrote caret, parenthesis, 12 times 5, parentheses. You wrote it differently, and so that way didn't. So rewrite that with one parenthesis going around the entire exponent. Very nice. Did it work? Okay, did it work? Okay. All right, wonderful, folks. So, big emphasis here. Make sure that you have one parenthesis wrapping your entire exponent together, because the parenthesis is like a bag saying, hey, here's the bag, and I want that whole thing to be the exponent. Okay, so what was part C then?
Double.
Yeah, part C is asking how long until you double your money. So now here's the really exciting one. We want to calculate a logarithm. So in part C, we're going to take this whole thing here, our equation, and say I want to double $500. So how much is double 500? 1,000. So I want it to equal 1,000. So I'm going to say I want that whole thing to equal 1,000. All right, there we go. Now again, that was just something you had to think about. You're saying, oh, how long until I double my money? That means that I want this whole thing to equal 1,000 because I'm starting with 500, so I double it to get 1,000. Now we isolate the exponential. We need to divide off the 500, which again, as soon as you divide that off, you should see the number 2 because you're doubling your money. What if there was a 3 right there? What question would you be asking? How long until you triple your money, right? Okay, so now we have this. Now we convert from exponential form to log form. So that would be log base 1.000625 of 2 equals 12t. Now, folks, notice here that I have written 2 equals the exponential. I really prefer to always, this is just me, I really prefer to always see it as the exponential equals the number, because that's just how I've trained myself to see it. So really what I would probably do is rewrite it as 1.000625 to the 12t on the left equals 2 on the right, because then it's my more obvious routine of drop down the base number, 1.000625, of 2 equals exponent 12t. So if you want to rewrite it first so that it's exponentially equals a number, that might feel more comfortable. Now, I'm going to rewrite this as change your base rule. So that's log 2 over log 1.00065. And then furthermore, notice, since this is a 12t, again, I'm not going to divide by 12. I'm going to multiply both sides by 112. So if I multiply this side by 112, that'll cancel with 12. I multiply this side by 112. Where does the 12 go? Yeah, it goes into the denominator. So there we go. That's time. That's how long I have to wait to double my money. Notice I did 2 steps here. That's a little confusing. I converted change of base rule into this fraction, and then I brought the 1/12 over and put the 12 in the denominator. It'll probably look better if you did 2 separate steps. So what do we get? Let's see, log 2 divided by 12 log 1.000625. And I got, wait, what did you get? 92.45? Well, fantastic. You'll all be dead. But if you wait 92 years, you would have doubled your 500 into 1,000. And again, probably better off getting a job, right, than waiting for that interest. But your kids will thank you for it. Actually, maybe your grandkids. The kids might be thankful by then. The grandkids. Sorry, maybe this is a little morbid. But I mean, 92 years to wait for interest, that's a long time, right? That's your entire lifetime. So, yeah. Great question. T is always years. The formula is based on years. It's always years. Okay, well, folks, we did a really nice job on number 1. We're not going to do, oh, no, we actually are going to do number 2 together. Because number 2 is a different problem. How many times are we compounding our interest? Continuously. So continuously, what is n equals? Infinity. So what they're saying is I want interest to be continuous, a constant stream of interest, not just hourly or minutely or secondly. I want continuous. And so this whole problem will be done using a equals PE to the RT. So let's go ahead and try this problem then. We'll use a equals PE to the RT, and we'll set it up the same way. All right, so number 2, we're going to start by writing the formula. A equals PE to the RT. Right, first thing, write down the formula. Second thing, diagram all your values. A equals, P equals, R equals, T equals. Why did I not write E equals? E is just a number. It's 2.71828182. It's not a variable in this situation. So let's look. $5,000 is invested, so that's my principal. And an account which offers 2.125% compounded continuously. So my interest rate is 2.125%, but you can't use a percent. It always has to be a decimal. So you move the decimal twice to the left, and so it's really 0.02125. Interesting note, in mathematics, you never actually calculate with a percent. You always convert to decimals. Begs the question why we even use percents. You never compute with a percent. You always have to convert it to decimals. So why do we even use percents? Well, yeah, you can convert it to a decimal. Yeah, I think as a society, we're just used to hearing things as percents. It's a communication tool. That's it. We communicate in percents. We don't compute in percents. So when you say something like 50% off, we all know what 50% means. It means you take off half. But then if you actually did a computation, you wouldn't write down 50% and plug that into your calculator. You'd plug 0.5 into your calculator because you moved the decimal twice. Okay, so there's our decimal, and it's compounded continuously. Okay, well, that's it. That's all the information we have. So part A says to write down a formula. So we'll just write down A equals 5,000 e to the 0.02125t. So that's just the formula. But all I did was just plug in 5,000 for p and plug in 0.02125 for r. But again, notice they said write it in function notation. So function notation would technically be a of t. equals 5,000 e to the 0.02. So that's function notation. You notice the formula is not given in function notation, it just says A. But you can write it in function notation by writing parentheses B. Okay, so now what's part B? Shall we do 5, 10, 30 again? Let's just do 5, 10, 30 again. So we're going to find A of 5, A of 10, A of 30. And in your calculator, it would be 5,000 e to the caret parenthesis 0.02125 times 5. Again, folks, make sure that the entire exponent is in a single parenthesis. So it's going to be parenthesis 0.02125 times 5 parenthesis. Let's see what you get. And go ahead and do all three. So let's check our answers. 5,000. Remember to get your E button, it's the LN button. We have to hit second LN and then there's your E. So A of 5 would be 55.60.50 cents. And then 61.83 cents. And 9,458.73 cents. Is that what you got on your calculator? I'm going to walk around real quick. Let me know if those aren't the numbers you got so I can help you on your calculator. That should be. But it's not. It's 0.02125. Oh, yeah, you have it right there. 0.02. There you go. Did it work? Sorry. Chelsea, did it work? Did it work in the calculator? Oh, Joseph? Right. Brandon? Did it work?
I didn't bring a calculator, but.
Oh, that's you. Okay, hold on. Well, yes, did it work? Okay, good. Isaac, did it work? Okay, okay. So folks, I just have a couple minutes left here, and we still have quite a few more problems in the packet, but according to the syllabus, our test is on Monday. Is it? Yeah. Yeah. So here's what we're going to do. First of all, I'm going to do one more problem with you right now. But then what we'll have left then is after these money problems, there's problems about growth and decay, growth of populations and decay of radioactive substances. They're still good problems, and they're the exact same. Like mathematically, they work the exact same. You're just plugging numbers into an exponential equation. So here's what will happen. On the test, these problems will be extra credit. Okay? So if you solve those problems on the test, you'll get extra credit for the same value of the points of a normal problem. So a problem is normally with 5 points. So if you do these problems, you get 5 points of extra credit. But also what I'm going to do is I'm going to go ahead and record myself solving these problems. So after class is over, I will just stay in the room and I'll record myself solving each and every single one of these problems. So you can always just go home, watch me solve the problems, and you can fill out your notes. That way your notes are filled out. And then when you also go home and look at your practice test, you'll see that I've also solved the practice test. So you'll have those practice test solutions as well. So in other words, what I'm saying is, even though we kind of ran out of time right now, I still think that you're perfectly capable of watching the video later, reading the solutions guide, seeing how to do these problems because they're applications of the same type of formula, and still doing it on the test. But as like my apology for the fact that I ran out of time, I'm making a bonus points instead of regular points. Does that sound like an okay deal? Okay, then let's finish our last problem because I think I have a minute, and I just want to help you set it up. Number 3. Number 3, how much money needs to be invested now in order to obtain $2,000 in 3 years if it's 0.25% compounded continuously? Yeah, we'll go ahead and do that. So, first of all, now compounded continuously, what formula are we going to use?
E.
Yeah, A equals PE to the RT. So let's diagram that. We've got A, P, R, T. What did the problem tell us? They said, how much money needs to be invested now? So my P is actually an unknown. I don't know. Brandon?
Well, for 2, we didn't do C,
Oh, you're right. We didn't even finish 2.
which is you telling that.
Okay. That's fair. Hold on. We're not going to do this one. Let's finish part C. Thank you, Brandon, for pointing that out. Part C, folks. I do want to finish that with you. So we have this formula, A equals 5,000 P to the 0.02125 T. And the question is, how long until you double your money? So what's double 5,000? 10,000. So we write down 10,000 equals 5,000. E to the 0.02125. And the very first thing you do is isolate the exponential. And when you divide off the 5,000, again, it's kind of a foregone conclusion. We'll get to number 2 because we're asking how long until you double your money. So again, I would probably rewrite this backwards. Well, to me, the normal way, which is e to the 0.02125 t equals 2. That way I have my exponential equals a number. So I can say base of the exponent equals answer. Convert it to log form. Log base e of 2 equals 0.02125t. And now, by definition, log base e is just ln, natural log 2 equals 0.02125t. And in this case, I would go ahead and just divide off the decimal. Right? There's no simple way to rewrite that decimal as a fraction and multiply by the reciprocal. So you just divide both sides by 0.02125. And that is the number of years until you double your money. Natural log 2 divided by that. Okay, your class is over. And I bet you we all want to check our answers. That would be, again, using parentheses correctly, natural log 2 parenthesis, divide by 0.02125. Did anyone else get 32.6? Yeah. So the answer is 32.6 years. Hey, that's in your lifetime. That's just, round about when you retire. 30 years from now. All right, well, thank you, folks. Like I said, I'm going to post a video of me solving all the rest of the problems. So you'll be able to watch that online. And that's it. See you Monday. On Monday, bring all of your practice packets for Chapter 5, Chapter 6. Bring your practice test completed. Did everyone get a practice test? Because I have some extras. In case anybody wants one. Anybody want an extra practice test? Yeah, Brandon? Anyone else? Got 2 more. Okay. How big did you want one? Yeah. Oh, okay, here you go.
I always end up printing out another one.
Yeah, sure. Thank you. Yeah, that's fine. In fact, that's perfect because I'm going to stay right here and record these real quick.
Guys, I'm going to show you mine. That's
You can show me right now. Oh, yeah, that's right, because I was. That's right, I'm just looking at what you got here. I see for number 5, you're writing plug in 0, but then what did you get? 6 over 6 equals 1?
Yeah.
I don't understand how that's the answer. Is that x plus 3, x plus 12? Is that an 11? Okay, I do need to see the test. Number 5 on the second part of the test. Oh, it's a 1. Yeah, that one needs to. We've done that. Okay, then. Right. That's not.
It's 6.
That's not 6. That's number 7. That's number 6. Yeah, number 6.
Oh, it's because I did it right on this one.
Oh, because you'd already done it. Oh, right. Okay. 7. Oh, okay. That should be something else. That's a 9. Oh, right. So, let's see what I put. Oh, because it's 7. Okay, yeah, that works. You started it and then you just didn't. You just need to finish it. Oh wait, did you finish it over here? Oh, you did finish it over there. Okay, and then finally, where's number 10? All right. Okay. So then, based on all that, then all you need to do is just number 5. If you want to do it right now, you can just Chantal. There you go. Chantal.
I have the